Good morning. My discussion will be based on the lecture videos that my professor shared. This video is for the chapter 1, which is the integration concept or formulas. The first shared video is differential and integral calculus formula, but I will focus on integral calculus formula. Integral calculus formulas. Number 1. The integral of dx is equal to x plus c. Number 2. The integral of a of f of x dx is equal to the integral of f of x dx where a is constant. Next, we have the integral of c sub 1 f sub 1 of x plus c sub 2 f sub 2 of x plus plus c sub n f sub n of x dx is equal to c sub 1 integral of f sub 1 of x dx plus c sub 2 integral of f sub 2 of x dx plus c sub n integral of f sub n of x dx. I will not further explain this because we will use this all if we solve integral calculus problems. Next, we have the power formula for integral calculus. These are the basic formula that we use for integral calculus, which is the power formula. These are usually used if we have polynomial function. So, we integrate them using this formula. Number 1. The integral of dx is equal to x plus c. It means, if you had an integral of dx, the function here is 1 because 1 is invisible, so the integral is simply x plus c. We'll always have plus c if we integrate indefinite integral unless it is definite integral. We have a limit number here. It will be definite integral, so we don't have plus c because we will solve the actual value. Next, we have the integral of a of f of x dx is equal to a integral of f of x dx where a is constant. Meaning, if we have a constant that is multiplied to the function of x, the integral of it is also equal to the function. You can move the constant a before the integral symbol. Next, we have the integral of c sub 1 f sub 1 of x plus c sub 2 f sub 2 of x plus plus c sub n f sub n of x dx is equal to c sub 1 integral of f sub 1 of x dx plus c sub 2 integral of f sub 2 of x dx plus c sub n integral of f sub n of x dx. Meaning, if you have more than one function, combinations of one or more function, you can distribute the integral sign and you will integrate each function one by one or equivalent to combine integral of each function one by one. Lastly, the integral of x to the power of n dx is equal to x to the power of n plus 1 over n plus 1 plus c where n is not equal to negative 1. Take note this n equals negative 1 because if n equals negative 1, this formula cannot be applied because if we substitute the negative 1 to the n, we have n plus 1, negative 1 plus 1 equals 0, which is undefined. We will use other formula if our n is equal to negative 1. Now we will solve some examples to illustrate the power formula for integral calculus. For the first example, find the integral of x squared dx. Our n here is 2, so x to the power of 2 plus 1 over 2 plus 1 plus c is equal to x cubed over 3 plus c. Next, we have the integral of x cubed dx is equal to x to the third power plus 1 over 3 plus 1 plus c is equal to x to the fourth power over 4 plus c. Lastly, we have the integral of 1 over x squared dx. This time, x squared is in the denominator. We will use this as an negative exponent. So, the integral of x raised to negative 2 dx, then our n here is negative 2. Therefore, we have x raised to negative 2 plus 1 over negative 2 plus 1 plus c is equal to x raised to negative 1 over negative 1 plus c or negative 1 over x plus c. 1. The integral of sine x dx is equal to negative cosine x plus c. Number 2. The integral of cosine x dx is equal to sine x plus c. Number 3. The integral of secant squared x dx is equal to tan x plus c. Number 4. The integral of cosecant squared x dx is equal to negative cotangent x plus c. Number 5. The integral of secant x tan x dx is equal to secant x plus c. Number 6. The integral of cosecant x cotangent x dx is equal to negative cosecant x plus c. Again, these formulas are derived based on basic derivatives of basic trigonometric functions. We will not use algebraic substitution or use substitution. Instead, we will transform the examples into this form of integral for us to integrate using this formula. Aside to this basic trigonometric formula for integral calculus, mostly the problems we must use trigonometric identities. So here are the basic trigonometric identities that we can use. Number 1. Sin x cosecant x is equal to 1. Number 2. Cosine x secant x is equal to 1. Number 3. Tangent x cotangent x is equal to 1. These three are called the reciprocal identity. 4. Tangent x is equal to sin x over cosine x. Number 5. Cotangent x is equal to cosine x over sin x. These two are called ratio identities. Number 6. Sin squared x plus cosine squared x is equal to 1. Number 7. Tangent squared x plus 1 is equal to secant squared x. Number 8. Cotangent squared x plus 1 is equal to cosecant squared x. These three are called the Pythagorean identities. Now, we will solve two examples. Number 1. The integral of 3 secant x tan x minus 5 cosecant squared x dx. We will apply the distributive property for integral, so since we have two functions, we can distribute this integral, so we have the integral of 3 secant x tan x plus the integral of negative 5 cosecant squared x dx. We can move the constants. We have 3 integral of secant x tan x dx minus 5 integral of cosecant squared x dx. This integral can be solved using the direct formula that we have a while ago. We have integral of secant x tan x dx is equal to secant x. So we have 3 secant x negative 5. This time, the integral of cosecant squared x dx based on the formula is negative cotangent x. So we have negative cotangent x plus c. Simplifying further, we have 3 secant x plus 5 cotangent x plus c. Next, we have the integral of 2 cotangent x minus 3 sine squared x over sine x dx. We will first simplify this integral. We will distribute this sine x. We have integral of 2 cotangent x over sine x minus 3 sine squared x over sine x quantity dx. Distribute the integral symbol, so we have integral of 2 cotangent x over sine x dx minus the integral of 3 sine squared x over sine x dx. We will move the constants. 2 integral of cotangent x over sine x dx minus 3 integral of sine squared x over sine x dx. Our first integral, we can represent it as 1 over sine x is equal to cosecant x. We will replace it to 2 integral of cosecant x cotangent x dx minus 3. We will simplify this. We still have sine x dx. We have a formula for integral of sine x dx, which is negative cosine x. Therefore, we can now solve the second integral. We have 2 times negative cosecant x minus 3 times negative cosine x plus c. To simplify, we have negative 2 cosecant x plus 3 cosine x plus c. Next topic is trigonometric formula for integral calculus. So this trigonometric formula for integral calculus is based on the formula for derivatives of the basic trigonometric function.